OK, so the title and abstract of my talk were a little bit general. So I'm going to try to cover a lot of material, which might be a bad idea. So this week, for these 2 hours, I'm going to mostly be doing basic stuff, just because what I would like to communicate to you is sort of a broader framework in which all of these recent lifting theorems that have led to a lot of new circuit lower bound, a lot of recent strong new circuit lower bounds. There's a lot of sort of deep theory that goes in behind it, and by deep I just mean that there's like a lot of stuff, basically. I don't think it's terribly, deep mathematics, but I also think that that these new theorems sort of shed light on old circuit lower bound theorems that existed in the literature. So I'd like to also sort of talk about those in the same light. In some sense, I'm now believing that more or less every monotone circuit lower bound, or if you're familiar with these sort of things in the literature, is more or less analyzing, doing a lifting type theorem, but without even knowing it in a lot of cases, even the results back from the 80s and the 90s. I'm going to try and give a unified picture of everything that's going on. But OK, so that means I'm going to have to start from basics. Yeah.
Just want to say that there's a confusion between deep mathematics and elementary mathematics, not elementary mathematics. Basically, deep mathematics, although it can be simply expressed.
Yeah. OK. That's the optimistic way of putting it. Thank you. Mathematical way of putting it. OK.
I thought he was going to say something else, which is if you need 3 weeks, just then.
OK. OK. So, so kind of the one picture that you could maybe take away from this talk, I think, is this sort of 3-way picture. So it's going to be what I'm going to be describing, generically speaking, is a 3-way connection between communication protocols, circuit complexity, and proof complexity. So there's going back for, because we have a pretty broad audience, I'll tell you what I mean by each of these individual objects over the course of this talk. But let me just say it for people who are familiar. There's sort of long-standing connections going back between communication and circuits with these Krushmer-Wigderson games, and between proofs and circuits with this feasible interpolation. And it turns out that there's actually a nice generic way that's kind of, I think, only been elucidated recently that shows that that all of these 3 objects are actually equivalent. OK? So let me start by just sort of describing the main actors, I guess. So maybe people here are familiar with the notion of a communication protocol. OK. So a communication protocol is going to be a method for solving some problem in a distributed environment. So it's a basic computational model that goes back to Yao in the 70s. So the basic setup is the following. You're going to have we have some task. Let's think of it as, for our purposes, it'll be useful to think of it as a relation. OK, on 3 parts. And we'll think of this relation as being sort of a task that's going to be solved in a distributed environment. So there's going to be 2 players, Alice and Bob. So Alice is going to get as input some input x from the first part. Bob will get an input y that's in the second part. OK? And then what they want to do is they want to decide between themselves whether or not there exists if there's something in the third part such that the triple is in the relation. OK? So this is kind of like a search problem, but again in a distributed environment. So of course, the only thing that's keeping them from sort of deciding this relation outright is the fact that Alice doesn't know what Bob's input is, and Bob doesn't know what Alice's input is. So the model is set up so that they're the basic primitive is for them to communicate bits of information back and forth across each other, and the complexity measure is to measure how many bits of information they need to communicate. Okay, so. this is, again, probably a definition we're all familiar with, but just so that we're all on the same page. So I'll define a communication protocol, but I'll kind of define it not super duper rigorously because many people are probably familiar. So a communication protocol for deciding a relation, like a three-place relation like this, is going to be given by a tree. And the tree is going to describe basically going from top to bottom, the bits that Alice and Bob are going to be sending back to each other. So each node will be labeled by a player, Alice or Bob. Each node, you have a bit, 0 or 1, that we think of as being sent across the communication channel to the other player, right? So, and of course, we don't make any restrictions on alternation. We're not going to make any restrictions on alternation. Like we don't need to have them play one at a time. Like Alice could send multiple bits in sequence if she wants to maybe send her entire input or something like that. And then once the players have communicated enough information back and forth to sort of agree on whether or not their inputs are in the actual relation, they can sort of halt and agree on an output. So maybe we could put in like a bottom symbol if it's not in the relation, or otherwise we'll just label each of the leaves of the tree with one possible output from the relation. So to be clear, Alice will get like an execution of this protocol at each node. Each node will depend, obviously, on the path that leads to the node and also the inputs that the players get. So like Alice gets to look at her input and then decide whether or not to send 0 or 1. If she sends 0, then Bob looks at his input. He knows that he received a 0. He decides whether or not to send back 0 or 1, and so on. OK? So
it's really a definition of the self problem, because this decision problem may be trivial if there is always a node.
It's true.
And so you
Yeah.
really want, whenever there is one, to produce one.
Yeah, this is a good point. Yeah. So we're not really just deciding whether or not this is yeah, okay, good. Yeah, thanks, Avi. So really, what I wrote down here wrong is that really what we're trying to do is factually find. We want to decide if one exists and also actually find one and output it if it exists. Okay.
So there's really no issue of uniqueness or non-uniqueness of that, like an O such that this interpolat's going to be X.
Oh yeah, no. There could be multiple. We just want to output one.
Okay.
Yeah. OK, cool. So a nice way to think about these things is in terms of when you just think about these protocols for a little, for a second, you kind of arrive to this understanding of them that every node is naturally associated with a combinatorial object, which is a combinatorial rectangle. So what do I mean by that? Well, we can just imagine describing this relation as sort of a matrix. Okay. So the rows of the matrix will be labeled with Alice's input. The columns will be labeled with Bob's input. And in each entry of the matrix, we can just write down a list of the possible outputs to this search problem, which are consistent with those inputs. Right? So now we can sort of draw like a very nice picture that describes what happens in this communication protocol in terms of this matrix. Right? So what do I mean by that? Well, let's just imagine what happens in this first step. Well, Alice is going to send a bit. She's just going to look at her input, and then she's going to send a bit 0 or 1 that decides what the next step in the protocol is going to be. So this corresponds to a partition in the matrix according to Alice's input, right? So if Alice's input is in this set, then she'll send a 1. And if it's in this set, then she'll send a 0. Right? And then, OK, well, if we go to the 0 side, well, now it's Bob's turn to send a bit. He's going to send a 0 or a 1. He knows that he's in this part of the matrix already because Alice sent a 0. So now it's a similar kind of partition, but now in the vertical side. So maybe it's now going to be either here or here, depending on wherever. And so maybe if Bob sends a 0, 0, well, now we know for everything in this area that there's not going to be an answer to this problem because we've arrived at this leaf. If we send a 1, it goes back to Alice, and then maybe it sends another bit. and then like another bit. And then similarly on the other side, we get a partition of the matrix in other ways. So what a communication protocol describes in a very natural way is a partition of this communication matrix that I defined just a second ago, the matrix which defines this search relation into rectangles. Okay, and I'll define what I mean by a rectangle, but it's just exactly what like an abstraction of what I just seen right here. And now at each leaf, each node, first of all, is going to correspond naturally to a rectangle. Those are just the set of inputs which reach that node. And each leaf will correspond to the set of inputs that reach the leaf will be a rectangle, and also every single input in there will have a shared consistent output. Right. Okay. So far, so good. Okay. Yep.
So it seems to me that finding this O, if there are more O's for some given X and Y, then it should be easier than if there are fewer O's. Is that something that we take into consideration?
It depends on the relation. It depends on the relation, but in general, that's like not a bad idea to have. Like what'll often happen is you'll have some inputs which overlap in lots and lots of O's, and some inputs which don't overlap in very many, and so on. Okay. Okay. So what we're going to be particularly interested in, this is a very general setup. What we're going to be particularly interested in is a case where there's actually always going to be at least one O. Okay? There's always going to be at least one output. So in other words, when the search problems are total. Okay? So for us, a total search problem is going to be a relation S, which is contained in X cross Y cross O, such that for every X and Y, there is an O. That's just saying that there's always an answer to the problem. Okay. Yeah, precisely. Yeah, yeah, because it will be functional in this case. So a deterministic communication problem will give you a function that's consistent with this. Yeah, that's right. Okay. So now, because of the way that these things are set up, and I'll say more about this in a second, it'll be useful to restrict things even further. So at the output of each of the leaves in this protocol, like we argued, every output corresponds to a rectangle in this communication matrix. So I'm going to be particularly interested where not only is there an O, but in fact each O will correspond to like a rectangular set in this X cross Y. So I'll define what I mean by that. So first, a combinatorial rectangle in X cross Y is any set of the form A cross B, where A is in X and B is in Y. Right? So it's just a cross product. Okay. And I'll say and now finally, this is going to be the rectangular search problem. A rectangle cover of U cross V. Maybe I'll move it down. is just a collection of combinatorial rectangles which cover every entry. Okay, so I mean, for a picture, if this is our U cross V, then there's a very, you could just imagine a bunch of combinatorial rectangles, which are all, they could overlap sort of arbitrarily badly, but in sum, they will end up covering every single entry will be covered by at least one member here. Okay, so if you give me a rectangle cover, there's a very natural search problem associated with it, right? Which is just given an input, output the name of any rectangle that that the input's contained in.
It's not currently happening in the picture, right?
Say it again.
It's not currently covered in the picture.
Oh, it is. Yeah. I don't know if I should color it all in. Yeah. Okay. So I'm gonna just kind of only be interested in these rectangle cover search problems. The complexity of total search problems is also interesting in its own right, but like for our purposes, it'll turn out that combinatorial the search problems that come from rectangle covers are really the interesting ones, and I'll actually explain why that's true in a little bit. Okay. But is there any questions about any of the basics that I've talked about so far? Oh, you totally can. Yeah. That's totally valid. You could absolutely do that. Yeah. But I mean, we're going to be interested in cases where it's not 0, 1, but absolutely you could. Yeah. OK, so I've given you all this setup. So what's kind of the motivation for all of this? Well, it turns out the motivation comes from circuit complexity. OK. So this is this Karshmer-Wigderson connection. OK. So in circuit complexity, we're given, we consider problems of the following form. So we're given a Boolean function, OK? And we want to understand what's the size of the smallest circuit that computes it. OK? So for us, circuits will always be over, say, and, or, and not. And we can also just assume that they're De Morgan, so all the nots are at the input. Right? So here's a really simple circuit which is computing some Boolean function. Okay? It's just the composition of all of these things. So we'd like to understand what's the minimum amount of hardware you need to actually implement these things. Okay? And the main message of this Karshmer-Wigderson connection is that understanding what the size of this, understanding complexity measures of this smallest circuit is equivalent to understanding the complexity of certain communication protocols for a related game. Okay, this is this Karshmer-Wigderson game. Okay, put that over here. Okay. So I'll write it as just a KW game. Okay. So what I'm going to define now is for any Boolean function, a rectangle cover associated with it, such that the communication complexity of the search problem for the rectangle cover is going to be equivalent to the complexity of computing f, in some sense. Okay. So this is a really remarkable, like a really quite amazing connection. So for any Boolean function f, okay, we can define a rectangle cover, which I'll call kw of f. Okay. Maybe I'll move it down. Okay. So what are the three parts of the relation going to be? Well, the first part of the relation will be the ones of the function. So Alice will get an input that's guaranteed to evaluate to a 1. Bob will get an input that's guaranteed to evaluate to 0. And what they want to decide on is an input on which these two inputs differ. So an input variable, an input index of this function, where the two inputs are going to differ. So I can write it like, so I'll write it like this. Okay. So let me define each of these guys. So for any input variable I, so I is an input index to the function. F is a function on n bits. And for any bit b in 0, 1, we can define x, I, b to just be the set of all pairs x, y, which are 1s or 0s of the function, respectively, such that xi is b and y sub I is 1 minus b. Okay. So for each input and each assignment to the input, we have all the pairs which distinguish between for which that input and that bit distinguish these two guys. So since every one of the function and 0 of the function, since they're different outputs of the function, they have to differ somewhere, right? They can't be the same input. There must be some input index on which they're different. And so what I'm doing is I'm just splitting it all up into all the input indices. So the fact that every single input has to be covered means that this is actually, it's total. Okay? And so a real question is why is this a combinatorial rectangle? And the reason is because these like x and y, whether or not they're in there, there's no correlation between the two sides, right? Like Alice can look at x and decide if her input is if the ith bit is b, and Bob can look at y and decide if the input is 1 minus b. They don't need to do any communication in order to decide that. It's total. Like they can each do each of their checks independently. Okay. Okay. Is there any questions about that? Okay. So what I'd like to prove now. So what I'd like to prove now is that, in fact, the depth of the smallest communication protocol that solves this Karsmer-Wigderson game is just the same as the depth of the smallest circuit, which is going to compute the function. Okay? So probably a lot of people have seen this, but what I'm going to want out of this theorem is more than just the depth. Well, we're going to argue something much stronger, which is, in fact, if you look at the communication protocol, the structure of the protocol is going to be isomorphic, like completely the same as the structure of the smallest formula that computes f. But I'll say what I mean by that in a second. Okay, so let's let f be any function. Okay. I'll say it like this. For any size s depth d, formula, computing f, there is a, I'll say, rather than worry about getting really technical, I'll just write isomorphic and in quotes. There is an isomorphic communication protocol solving KWF and vice versa. So solving this communication problem, this Karpman-Vagerson game, is equivalent to computing F. And we can actually prove it. Okay. Okay. So first, let's start with a formula and produce a communication protocol. So we could start with, say, this formula. Okay, so I started with this. So I have a formula which is computing some Boolean function, and I want to come up with a communication protocol which is solving this problem. So Alice gets a 1, Bob gets a 0, and they want to decide an input bit where they're different. They want to actually find an output, an input bit where they're different. Okay, well, Alice and Bob have no restrictions on themselves in terms of computing, so they can both imagine that they have the formula in their minds. Okay. So what they'll do is Alice will just take her input and evaluate this whole formula on it. Okay? So let's say Alice and Bob. Let's say Alice has a 1, so 1, 1. Okay, so the and of 1 and 1 is 1. That's also 1, and so we get a 1 at the output. Maybe I'll use a different color. And now Bob, on the other hand, will have a 0. So this has to be 0, 0, 0, 1. So we get 0, 0, and 0. Okay. So they both privately look at their inputs that they receive, and they evaluate the whole formula on it. And now, to solve this communication protocol, what they're going to do is they'll start at the root, where they know there is a difference on their inputs. And depending on what the gate is, if it's an AND or an OR gate, they'll communicate to each other where they should go next. Their goal is to get to a leaf where they're actually different, and this will tell them both the name of the input and also whether or not it's negated.
Robert, that left internal node for Bob evaluates.
Oh, yeah. Oh, well, OK. Depends on. Thank you. Whatever. OK, well, now it's really easy because they can just pick anything. But whatever. OK, but let's do it anyway. So we start with the AND gate. At an AND gate, well, Alice has a 1 of the function and Bob has a 0. So in order for Alice to output 1 here, both of the inputs must have been 1. So it doesn't matter to her where they go. She's always going to have the same answer. Bob, on the other hand, he has a 0. And for an AND to be 0, only one of the two inputs needs to be 0. Right? So what's going to happen whenever we're at an AND gate is Bob will talk, and he'll send Alice to whatever input node that he received a 0 from. If they're both 0, he'll just say the left one, something like that. So we could do so then at an OR gate, the dual thing happens. So if we're at an OR gate, well, now Alice gets the 1, so she knows where her 1 must have come from. Since Bob has a 0 evaluated here, then both of his inputs must have been 0. So Alice will look at her 2 inputs and send where the 1 was. So like she could say, OK, right here, there's my 1 right there. Right? So then Alice will send back. And then at each of the leaves, well, we just output exactly what the outputs of the leaves would be, right? So this would be x1, 0. This is x2, 1, x3, 1, and x4, 1. Okay? So we see that not only is the protocol tree that gets produced, like, it has the same depth, it also has exactly the same topology. Everything is connected in exactly the same way. Like, really, a communication protocol for this Karpman-Wigderson game is just taking this circuit and relabeling AND gates with Bob and relabeling OR gates with Alice. Right? So there's a very strong connection between these two directions. So this direction is easy. Okay. So for the reverse direction, still pretty straightforward. Okay. So the reverse direction will just go by induction. So instead of going from the top down, we'll go from the bottom up. Okay. So we're going to start now with a protocol that computes it, and we'll inductively construct a formula that's going to compute the function. Okay. So we'll do induction on depth. Okay. Well, first of all, let's consider the case where the depth of the communication protocol is 0, right? Where it's nothing. In that case, I mean, the protocol is just, Alice and Bob don't even look at their inputs. They just output an answer, right? Because this is the weird case where the entire protocol, where the entire matrix is just contained in one rectangle from the cover. Okay? So d equals 0, they just output the name of the rectangle. And I mean, just by our connection from before, well, you know, we can just replace that rectangle with whatever the corresponding variable is. The function is just like a 1. It's just a variable or its negation. Okay? So now, by way of induction, well, let's suppose that Alice speaks first. Okay? Okay. Well, if Alice speaks first, well then, for each of these two smaller depth protocols, what we can do is, by induction, turn them into formulas which compute which compute sort of a partial function. So what do I mean by this? Maybe I'll move this up. Okay. Okay. So Alice is going to speak first. So by what we said before, I mean, if we give Alice the rows and Bob the columns, then this is going to partition the matrix into two pieces. Okay? So now let's remember that these are really just labeled with 1s of the function and also 0s of the function. Right? So the rows are labeled with 1s, the columns are labeled with 0s. So now inductively, what we get is one circuit which will be correct on all of these inputs right here, all of the inputs that are correct up here. This is say the inputs in which Alice sends 0 first. And we'll get a second formula on which the circuit which is correct on all the things where Alice outputs 1 first. Does that make sense? Because I mean, you know, clearly if I start from here and I just apply the reduction, I'm not going to get I won't get a formula for the total function. I'll just get a formula for the function restricted to being under the subject to the restriction that the inputs are whatever Alice was sent first. Okay. So we can just define two functions then. So it'll be so the restricted functions say when Alice sends a 0 first. Well, it'll always output 0. It'll output 1 if f of x is 1 and Alice sends 0 first. And otherwise, it'll be a partial function. We just don't care what it outputs. OK? So by restricting to this, we will for sure get a formula that computes this function, which is now a partial function. We don't know what it's going to say on these guys. And the same things with the 1s. So it'll again be 0 if fx is 0. It'll be 1 if fx is 1. And Alice sends a 1. And otherwise, we don't care what it outputs. OK? And you can just see that, OK, well, f1, this is going to compute the function f1. f0, once we do the thing by induction, will compute the function f0. And I mean, it's very easy to see that f is just exactly f0 or f1, right? Because any input has to either be, Alice either has to send a 0 or send a 1. Right? So all we do is we just take the, so the final formula will just be f0 or f1. Or to put it another way, just do the exact same thing we did a second ago. Take all the Alice nodes and turn them into ORs, and take all the AND nodes and turn them Bob nodes and turn them into ANDs. And we get exactly a formula of the exact same topology, exact same structure. Okay? So the main message of this theorem, I think, is really just that formulas and communication protocols for this problem are like the same object. Like they're exactly the same. There's any information that you could read from one, you can read from the other. It might be useful to look at one for another for different purposes, but mathematically, they're totally equivalent. Yeah?
Yeah, so yeah, they're totally equivalent. I must say that for us, when we formulated this very simple result, the main message I think to take home is that circuits are naturally objects that you look at bottom up. They take the inputs and they compute. And we tried to, at the time, prove low bounds for graph conductivity on monotone circuits. Doesn't matter. And we just couldn't. And because of this equivalence, we, somehow this allowed us to view it as a communication complexity problem as a top-down, where one could formulate some inductive assumption going down that was meaningful because it talked about 0 and 1 of the function that we couldn't. We just had no access to in the bottom-up situation. Yeah.
Yeah, I agree. They're mathematically equivalent, but that doesn't mean that that one is easier to prove things about than the other, right? So this is I guess like a way of rephrasing your point, Avi, is that like even though this is almost, it seems like a very simple result, it's extremely profitable from the perspective of trying to understand what's going on with these things. It's very, very useful for trying to prove results because somehow communication protocols are easier to think about from a top-down perspective than circuits are from the bottom up. Okay. Say it again.
Where did you use that in the formula?
Oh, it's just that we never reuse anything. We're always proceeding, like this proof always proceeds from the top down, so you're always going to exactly one place in the same thing when you're going from the bottom up. So you're never actually going to go to a gate and reuse it. Everything is a tree.
But there's a version for virtual circuits.
There is a version for circuits, and actually we'll get into that. Yeah. OK, cool. OK. OK, so now a lot of these. So this is very, very useful. So unfortunately, in circuit complexity, we don't have any lower bounds for non-monotone circuits, so for circuits with not gates. So a lot of effort has gone into understanding what's going on with monotone circuits first. So that's cases where the circuit is where the circuit has no negations, and so the functions will be monotone. I'll write all this down. I'm just sort of prefacing it a little bit. So what I want to motivate to you now is what's natural about the monotone case. And now, I mean, one thing, it's obviously very natural in the sense of I can't prove something, let's make some restrictions on the circuit in order to try to make something, and maybe we can turn off this restriction later. What I want to argue now is that actually the monotone functions are very natural from a communication complexity perspective because every rectangle cover is equivalent to a monotone function. So what this means is that if you wanted to prove any lower bounds in communication complexity for rectangle covers, you would necessarily be proving monotone circuit lower bounds, right? So in some sense, monotone covers, they contain like all total search problems that are rectangular. So in order to prove any lower bounds, you would end up proving lower bounds for them at some point. Okay, so it's a very natural place to begin if we want to understand these games, because it's very natural to first understand any rectangle cover and try to prove lower bounds for it first, and then maybe we can make progress towards proving lower bounds on more structured covers. Okay. So, all right. Maybe I'll add it right here. So a Boolean function f is monotone if okay. So already like this, x is less than y means f of x is less than f of y. This first less than is on strings. It just means that bitwise. Bitwise, every element of the first string is less than or equal to the element of the second string. So in other words, flipping a bit from 0 to 1 cannot make the function flip from 1 to 0. Okay? And many natural Boolean functions are monotone. I mean, clique, ST connectivity, majority, like many, like almost like lots and lots of the functions that we normally consider are monotone. So, okay, so once we make this restriction, however, there's a very natural restriction to make on this Karpov-Yggdrasil game. Okay? And the natural restriction is the following. Well, if I have an input x, which is a 1 of the function, and I have another input y, which is a 0 of the function, certainly there's a place where they have to be different. But moreover, there's going to be a place where x has to be a 1 and y has to be 0. Right? Because otherwise, y would be less than x, or sorry, x would be less than y, and then y would be 1. Right? Does that make sense? So if f is monotone, then this just means that there is an I such that xi is 1 and yi is 0. Because otherwise, x is less than y. And by the monotonicity, we would get that y is a 1. Okay. So this suggests that there's that we can actually remove some of these rectangles and still get a rectangle cover. Right? So running out of room a little bit. But so maybe I'll put it over here. So I'm going to define MKWF to be the monotone Karpov-Yggdrasil game. So it'll again be a search problem or a rectangle cover for our purposes. Okay, so now we just have the rectangles which separate things in sort of the positive way. So it's going to be all pairs x and y, such that xi is 1 and yi is 0. Okay. And then we can define MKWF as a relation. I like to think of it as just like the collection, the actual rectangle cover itself, like the collection of rectangles. Okay. So this is certainly, so it's still a rectangle because these guys are rectangles, and it covers everything for this fact. Okay. And getting back to Yash's point a second ago, where one immediate way to see that this game should be harder in a communication complexity setting is that inputs will have less answers. I'm no longer asking you to find just a place where they're different, Now I want you to find a place where they're different in a particular way. So the 1 input is actually 1, and the 0 input's actually 0. So this is actually like a harder game to solve, not an easier one, right? So we should expect it to be easier to prove lower bounds. And in other words, monotone lower bounds should be easier to prove than non-monotone lower bounds, which agrees with what actually happens in practice. OK.
Does the same equivalence hold monotone circuits or same as?
Absolutely. Yeah, that was going to be my next point. So this exact same theorem holds with this isomorphism. Like if you just replace monotone Karchmer-Wigderson with Karchmer-Wigderson everywhere, and if you make the formulas all monotone, so you just don't put negations anywhere. And that's not hard to see. I mean, the exact same proof works. You just erase all these negations. You just never get this flipping occurring at the leaves. Okay. Any questions about that? OK, so I want to state this sort of proposition, which is really, really easy, but I think it's, I don't know, not known or maybe underappreciated. OK, and it's basically going to say that, just what I said in words a second ago, that monotone Karchmer-Wigderson games they characterize all rectangular search problems. Like every rectangle cover is equivalent to the monotone Karchmer-Wigderson game of some function. Okay, so and I mean this in a very, very generic sense. So let's let R be a rectangle cover of just 2 sets, an arbitrary cross product, v cross v. Okay. Then there is a partial monotone function. I'll say what I mean by this in a second. Okay. Such that R is equivalent to the monotone Karchmer-Wigderson game of F up to just relabeling elements. So, and the number of variables of this function is going to be exactly the number of rectangles which are occurring in the cover. Okay? So now, there's one strange thing here, which is a partial monotone function. I've only alluded to partial functions so far. So a partial function is a function in which we don't care sometimes what the function outputs. Okay? By a partial monotone function, I just mean that there's some monotone function that this can be extended to. Okay? So I can obviously extend it to a non-monotone function, probably, but there's also some monotone function that I can extend it to.
The same as having not having any zero about any one.
Say it again.
It's equivalent to not having any zero about
Yeah.
any one.
Yeah. OK. So the proof is really simple. It's just a proof by picture.
So now your game is a promise problem. So you're given an extra zero input, an extra one input.
Yeah, but I mean, that's true even for this case anyway, right? It's a promise problem in the sense that you're getting a, a 1 and a 0. There's nothing really different here, yeah, right? Really, it's just a question of what's the domain. You get an input from the domain in both cases, yeah. OK, so maybe I'll say up to relabeling.
Sorry, what's the definition of size of R again?
Sorry?
What's the definition of size of R?
Oh, just the number of rectangles in the cover. Yeah. R is just literally a set of rectangles, just the size of the set. OK. So, well, first of all, I mean, one direction is, going this way is easy. I mean, every monotone Karchmer-Wigderson game is a rectangle cover, so the interesting direction is the other way. So how does this work? Well, let's just do a really simple case. Maybe this is like 1 rectangle, and then you get 2 rectangles and 3 rectangles. OK, so this guy has 3 rectangles. So how do I come up with a function? Well, there's kind of only one way to do it. So for every u in the u domain, I'm just going to write down the list of rectangles that u corresponds in like unary. Okay? So if this is rectangle 1, this is rectangle 2, this is rectangle 3, we see that this little u is contained in both 1 and 3. So this is going to map to this string, say 1, 0, 1. Okay? Now for every v, I'll just write down the list of rectangles that it's not contained in. Right? So it's not contained in the first one, but it is contained in both of these. And we can see that the place where they intersect, the rectangle that they're both contained in, which is the third one, corresponds to exactly the place where the two input strings differ. Right? So in general, u maps to, say, like u is in R1. Like this string in Rn. Oops, not that R. Right. And now what I'll do is I'll just define the function to be 1 on these inputs and 0 on these inputs. Okay. So f of x will just be 1 if there is a u such that u maps to x, 0 if there is a v such that v maps to x, and star otherwise. So we obviously have to prove that this is actually a function. Okay? But that's actually easy to see, because if two guys, both u and v, were mapped to the same place, right? If they were mapped to the same string, well, then that means that u would be, let's say u is contained in all the rectangles, and v is not contained in any rectangle. Well, that violates this being a cover. That means that like these rectangles don't actually cover every input. They must miss at least one of them. Right? So this is actually definitely a partial function. Does that make sense? Is there any questions about that? So this result is really important to me. It says that like the communication complexity of rectangle covers is equivalent to monotone circuit complexity. So if you want to prove any lower bounds at all on communication complexity for total search problems, you're going to be proving lower bounds on monotone circuit complexity in the first place, right? And from the other perspective, from the perspective of proving circuit lower bounds via this approach, this suggests that monotone problems are like the hardest problems that we could hope to prove for. Like we can't hope to find a harder problem, so we should start by proving lower bounds on these ones, like the hardest ones. Does that make sense?
Can you also go the other direction? Like if you take click versus coloring, can you find a reasonable search problem?
Well, yeah, sure. I mean, given a clique and a coloring, just find an edge which is violated, right? Yeah, there's lots of cases of that. So probably now is a good time to take a break, but for the next part. But is there any other questions before we take a break?
You should probably show how a non-monotone
Oh.
is a monotone problem.
Yeah, good, great. Yeah, great question. OK, well, yeah, what happens when you apply this transformation to a non-monotone cover, right? I mean, obviously something has to happen, because every problem is a partial monotone function. Well, OK, let's just think about what happens. I'm going to start with a non-monotone function. So this is going to give me, by this Karpov-Yggdrasil game, a list of rectangles. Right? Right? So now we can just take this transformation and apply it to this rectangle cover and see what we get at the end of the day, right? Well, OK, well, I mean, this new function, maybe I'll call it f super m. OK? Well, the number of rectangles here is 2n, right? Because I have one for every positive literal, one for every negative. So the number, by this transformation, the number of variables in this new function is going to be 2n. Right? Now, well, what could this possibly correspond to? Well, it's actually a partial function. Well, every variable of this new function is going to have one variable which corresponds to like x, xi, and one variable which corresponds to like not xi. Right? And this function will only be defined on the inputs where, so if we write f as f sub m is like x1, x2, xn, y1, y2 to yn. Okay? This function is going to be a star whenever these guys don't actually correspond to a total assignment before. Whenever like y sub I doesn't equal to not x sub I. So let me just write that. So f sub m of x, y will be equal to 1 if y is like the negation of x and f of x is 1. It's going to be equal to 0 if y is the negation of x and f of x is 0. And it'll be equal to star otherwise. Okay? So in particular, when y is not just the negation of x. So what this means is that you've taken this entire non-monotone function and you've just embedded it in the middle slice, basically. So this is another way to get to this. Maybe people have heard of this connection with slice functions of monotone complexity. This is like another way to get to it. So this shows that the monotone complexity of functions that are completely embedded on the slice that only take sort of non-trivial values on this middle slice is just equivalent to to non-monotone circuit complexity. Does that make sense? OK, maybe now's a good time for a break then. So now I'm going to talk about the third leg of this picture that I drew and have erased, which is like where do proofs come into all this. Okay, and then I'm also going to talk about why I think that this is like a motivating thing. Because so first of all, just to talk about this for just another second. So this is a nice thing because it says the problem of coming up with hard monotone functions reduces to the problem of coming up with hard rectangle covers. And now, at first, that seems like maybe we haven't done much at all. But in fact, I actually think it's a useful step because rectangle covers are like a really combinatorial object. And it's going to be, it'll turn out to be easy to come up with sources of hard rectangle covers just by using tricks like composition and tensoring and things like that. So we'll see that in a little bit, hopefully. But first, I want to talk about where proofs come into all of this. Okay? So let me start by giving a very OK, so maybe I'll start with an example. Probably an example that everyone's seen, but it'll be helpful to jog people's memory. So let's start with an example of a simple proof system. So I'll start by talking about resolution. So the resolution proof system, it's a system for refuting unsatisfiable formulas. Okay? So as input, we're going to get an unsatisfiable CNF formula. And we want to actually prove that this formula is unsatisfiable. So we will prove that C is unsat by basically deducing a contradiction from it. Okay. So now resolution is a deductive system, by which I mean it's a proof kind of in the standard textbook proof sense. Like it's there are input, like there are lines to the proof, and given some subsets of lines, you can deduce new lines from it. Okay. So maybe I'll just say that the lines of the proof. So resolution is a very special system in that every line of the proof is going to be restricted to just be another clause. So we can only use inferences that are based on clauses. Okay? And the standard definition of the system has two rules: the resolution rule and the weakening rule. Okay? So the resolution rule says if I have C or X and D or not X, and C or D have no other opposing literals, right? Then from this, you can deduce C or D. Right? And this is clearly a sound rule because, I mean, for any assignment to X, either C is true or D is true. Right? And now the weakening rule, for completeness, you don't actually need it, but it will actually be useful just for the sake of proving things. It just says that if I have a clause C, I can deduce any clause C or D. Right? Again, supposing that you don't just like throw in sort of stupid stuff. Okay. So if you'd like to see a simple example, so one particularly nice example of a formula, of an unsatisfiable formula, is like this following formula, which encodes like the induction principle. Right? Okay. So it says that x1 is true, and if x1 is true, then x2 is true, and if x2 is true, then x3 is true, and x3 is false. So it's basically just encoding induction. Right? Well, how can we refute this using resolution? Well, it's pretty easy. I mean, we just resolve these first two terms on x1, and we'll end up with the clause that just contains x2. We'll resolve both of these on x3 and get not x2. And then we resolve both of these, and we get the empty clause, which has no satisfying assignments, and so it's a contradiction. Does that make sense? OK. So resolution is kind of like the simplest proof system, or one of the simplest proof systems that's studied in propositional proof complexity. Propositional proof complexity is like the area it's sort of a circuit complexity with the whole goal focused at proving NP is not equal to co-NP, to give it like a one-line summary. But as we'll see now, the idea of a proof is actually very much present in all of these communication protocols and also the circuits in this Karsper-Wigderson connection. OK. So I'm going to give now a very general definition of a proof system. I'll call it a deductive system. I'm going to call it a deductive system instead of a proof system because I want to allow it to be over, not necessarily over just Boolean assignments or anything, just over arbitrary domains. OK. So what's a semantic deductive system going to be? Well, we'll have some ground set. I'm going to use a curly U. So be like a universe. So you could think of it for concreteness as being like the set of all Boolean strings in the case of resolution. Okay. And I'm going to have another set, L. This will be a family of functions over U. And you should think of this as being a set of allowed lines. So in the resolution case, this will correspond to, it'll turn out to correspond to all the cubes, all the subcubes of 0, 1 to the n. Okay? And now finally, if I have A, B, and C, which are each allowed lines, I'll write A and B imply C if C is contained in A union B. Okay? So these are functions, but I'm thinking them as sets. Okay? Hopefully nothing complicated here. Okay? Okay. So this is soundness, basically. This is just saying that this is like a sound deduction. So if you think about it from a sort of a standard proof system kind of view, what this is saying is that if I know that A is true and B is true, then C is necessarily true. Sorry. I always get backwards. I'm thinking about things in terms of contradictions. If I know that A is false or B is false, then I know necessarily that if I know that something in C is false, then I know that one of these things are false. Sorry, backwards. I'm going to do that like a million times, so I'm really sorry in advance. Okay. And now, if we're given A1, if we're given a set of lines, which we'll think of as like axioms, okay, such that the union of A sub I is going to cover the whole universe. Okay? Then an L proof of U is just going to be a sequence of lines So everything in the sequence will be a line. Okay. The first n guys, so B sub j will just be the input axioms. Okay. The last guy will actually be everything. So we're proving everything. And finally, every line that's not an axiom is going to be a semantic deduction step from earlier lines. Such that B sub I and B sub j proves B sub k. I mean, equivalently, I could have just written this. B sub k is contained in both of these, but I like to think about it as like an actual proof system, so I'm going to write it with this sort of proof notation. Okay? Okay. So this is a very, very general definition of what a proof system could possibly be. So let me give some examples first. So as I kind of argued a second ago, semantic resolution, which it turns out is just the same as regular resolution, or just resolution, is going to correspond to the case where the universe is the set of all Boolean strings, and the lines will be all subcubes. So by this, I just mean conjunctions. So conjunctions ands of literals. Okay? So this is a little bit weird because when I was defining resolution, I defined everything in terms of clauses. But the connection is made when you just say the cube associated to every line will just be the negation of things at the line, right? So what this means is that when I take like the and of all the assignments that falsify this thing, that's going to be the entire universe, right? Or in other words, the union of all the guys is going to be the universe. And then given two guys, I can deduce a new one as long as it's contained in the intersection. When I negate everything, that just corresponds to it being a sound deduction. And then the final step being the contradiction. If we think about the set of inputs that falsify 0 equals 1, that's everything. So the final step is just the entire universe. Right? Does that make sense? OK. So the one thing that's different is that instead of allowing just deductions by these two syntactic rules, we actually allow any semantic deduction. It turns out for resolution, these two systems are the same. Like for resolution, if I allow arbitrary semantic deductions, you can simulate it by this with essentially no blow up. And the reason is just that cubes are very weak, more or less. Like if I have two cubes and I want to deduce a new cube that's contained in the union of them, well, the only interesting cases are basically this one, right? Because if I have like two complementary literals, then they'll actually be like disjoint. So you can't deduce anything interesting from it. OK, so another maybe more non-trivial example from the literature is cutting planes proofs, if you're familiar with optimization. So once again, I mean, really you could take it to be a bigger universe, but say for refuting CNFs, we can consider the universe to be these guys again. And now the allowed lines will be integer linear inequalities over the reals. Okay? And then given two integer linear inequalities, I'll allow you to deduce a new integer linear inequality. And this is, again, the semantic case. You can define a syntactic version of cutting planes, which is sort of forms the basis of a lot of these optimization solvers, these like branch and bound solvers. Yuval, thanks to paper of Yuval, we know that semantic is actually stronger than syntactic in this case. But it turns out that the semantic case will still be very interesting for us. Oops. Now, there's one more very interesting example of a semantic deductive system. And it's on the board. And that is a communication protocol. Right? So that are solving rectangle covers. So I'll say like cal_r. Well, now, what's the universe going to be? Well, the universe is going to be whatever just the cross product, whatever our whole space of inputs is. And the interesting lines, these are just going to be combinatorial rectangles. Over U cross V. And then using exactly the same usual deduction rule, the semantic deduction rule. Okay? And I'll prove to you now that, in fact, if I take a tree-like semantic deductive proof over these things, it's equivalent to a communication protocol. Okay? And as a second comment, all of these results about lifting or hardness escalation that you've seen in the literature, this is what's really going on in behind. So what they're doing is they're showing how to prove lower bounds on communication protocols by starting with lower bounds on these systems, simpler semantic systems, and transforming this domain and these lines into this domain and these lines in a structured way. So showing that basically the best thing you can do in this proof system is the best thing you can do in this proof system.
So resolution is the same as decision trees?
DAG-like decision trees. Yeah, but yeah. OK. So let me prove that now.
Communication protocol for R?
But I just mean for rectangle covers. Yeah. Like we're doing everything subject to rectangle covers. I just wanted to emphasize that fact. But
It's not that you're taking only the rectangles in R.
no. This is just all combinatorial rectangles over U cross V. The input axioms will be like the rectangle cover that we start with. Yeah. OK, let's do this right here. So here's another very simple theorem in the style of Karchman-Wigderson, which is just going to say that tree-like rectangle proofs. So by a rectangle proof, I just mean like this semantic proof system, are just the same as communication protocols, deterministic communication protocols. And I haven't said over there, up here, what tree-like means, but it means the natural thing. It just means that if you ever deduce a new line in your proof, you can only use it once. So if I drew the dag of this as a tree, if I drew the dag of this, it would actually be like a tree. OK? So once again, one of these directions is easy and one of the directions is hard. So taking a communication protocol and turning it into a proof turns out to be the easy case. OK? Well, how does it work? Well, remember, all we've been saying before is that like a communication protocol is basically just you start with, at the root, I'm going to cover all the inputs because the protocol is correct. It'll be correct on every input. And then every communication step is going to correspond to sending a bit and partitioning things, right? So maybe I don't want to go into the details because I basically already did it with Karchman-Wigderson games. But like this is just a proof where I've turned it sort of upside down, right? At the leaves, all the leaves of this will be labeled with combinatorial rectangles. These are the input axioms, right? And then if I view a communication step from the top down, if I instead view it from the bottom up, I'm just taking two of the rectangles and deducing a new rectangle that is in the union of the two of them, right? That's most easily seen by this step. Like here, like the first step of the communication protocol is going to split the communication matrix in half. When I do that step in reverse, well, I'm just taking these two rectangles which cover part of it, and the whole matrix is contained in the union of them, right? So the interesting direction is proofs into protocols. OK? And once again, we'll go by induction on the depth. And once again, the d equals 0 case is easy. It's just everything is contained in one rectangle, so we just output whatever that rectangle is. OK? So the interesting case is the following. So suppose that we have two rectangles in my proof. Oh, maybe I'll use b's. b1, b2, and we're going to prove b3. So b3 is contained in the union of b1 and b2, right? So here's my b1 and here's my b2. Okay. Well, there's only a few cases to consider. Okay. So remember that what I want to come up with is a communication protocol. So here's a picture of like the proof. Okay. So starting from this line, we've done some work down here to do these, and then we're going to deduce this. So by induction, we can transform both of these into communication protocols that work for b1 and b2. Okay? And now we want to come up with a communication protocol that works for b3. Right? Well, we just have to consider where b3 lies. We know b3 is in the union of these two guys. Well, for the first case, I mean, if b3 is just completely contained in one of them, then the communication protocol is easy, right? You just run the protocol for b2. Right? Since it the protocol for B2 works for all of these inputs. It will also work for anything that's completely contained in it. So the only interesting case is when it's actually non-trivially contained in the union, right? It's contained in both of them. But these things are rectangles, right? So there's only a certain ways in which this can actually occur. And there's two ways, right? You're either going to have something that looks like this, right? It's either going to be that, or you're going to have something that looks like this, right? In other words, there can't be two inputs in B3 where something is like up here and something is also down here, right? Because B3 is a rectangle. Here we're using the fact that all the lines are combinatorial rectangles. If both of these points were in B3, then these points would also have to be there, so it wouldn't be contained in the union anymore. Does that make sense? So the main point is that so B3 is either contained in the intersection of rows of B1 and 2, or it's contained in the intersection of the columns of B1 and B2. Right? And now, if it's contained in the intersection of the rows, well, then our job is easy, because it just tells you who to speak. Right? So in this case, I'm contained in the intersection of the rows. So it's the column player's job to tell you which protocol I should run on either side, right, from the top down. And if it's contained in the columns, then it's the row player's job to tell you either run the protocol or run the protocol. Right? So this tells you exactly what bit to send. Either run the protocol for B1 or run the protocol for B2. And the person who speaks depends on whether or not it's contained in the intersection of rows or the intersection of columns. Does that make sense? OK. Cool. And it should also be clear that everything is a tree because we're doing everything from the top down and everything is being expanded. So it's all good. OK. So in the last 20 minutes of today, I want to talk about the connections between basically why I think that this is like a motivating example. And so if we go back to just a second ago, we were talking about rectangle covers. And we now know that proving lower bounds is equivalent to finding hard rectangle covers and proving examples of them. And the way that we will prove lower bounds on hard rectangle covers, and it turns out the way that basically every example in the literature on monotone circuit lower bounds, I think in fact all except one or two, are secretly proving lower bounds by starting with a hard problem here in one of these systems, starting with a hard CNF formula or a hard search problem somehow over these systems, and transforming it into a hard rectangle cover over these systems by basically very simple transformation. Okay? And then the whole work is in proving that somehow this inherits the hardness when you do this transformation. Yeah?
Does it include the approximation method?
Yeah, sort of, yeah. I have some thoughts on that, but yeah. Yeah, more or less. Yep?
So when you drew your triangle of communication process circuits, for proofs to communication, you have the semantic deductive systems, and then communication and circuits, you have the Karshman-Radisson game. And then what is the connection between proofs?
It's transitive.
So it's not a triangle, it's just communications in between.
Well, they're all the same object.
Through communication.
I mean, like the takeaway is that they're all mathematically equivalent. They're all the same object, right? So we prove that communication protocols are equivalent to formulas. Here we're proving that actually, yeah.
Go via the communication, right?
You can go. I mean, you could also prove it. You could prove it directly if you wanted, but yeah. I mean, yeah. If that's the way that you like to think about it, then yeah, sure. But I mean, the real message is that they're all the same object.
Like resolution and decision tags, this is also standard.
Also standard? What do you mean?
Give those where you.
Oh yeah, sure. Yeah. That's true. I mean, like, if in the resolution world, I mean, the corresponding object to a communication protocol will be like a query complexity model. So a tree like resolution will correspond to a decision tree, and like a resolution proof will correspond to what's called a decision DAG. Okay. But OK, that's exactly what I want to talk about now. So let's start talking about it. OK. So the goal now is going to be we're going to start with a hard problem for a simple deductive system which you could think like resolution. And we want to transform it into a hard rectangle cover. OK? So I think it's very profitable to start thinking about resolution in this case. So the starting place is just for resolution or in standard propositional proof complexity, the universe that we're working over is always Boolean. Okay? And the interesting cases of the hard inputs, like the hard contradictions, are usually CNF tautologies. Okay. So that just sort of suggests a question. So if we're given a CNF contradiction, how do we construct a rectangle cover from it? Right? And I mean, I would claim that there's, if you just think about this for like, if you think about it for like 5 seconds, there's one very natural way, which is just take a partition of the variables. Right? So this thing is going to be over some set of Boolean variables, z1, z2, up to zn. One is going to be partition variables. Okay, so into, say, z1 cross union z2. Okay, so you could take the variables of this. You could partition it into 2 sets. This will induce a partition on every clause, right? Every clause will now get split in half. And it's easy to see that the set of assignments which falsifies one of these clauses is a rectangle, right? So this means basically what we're doing is we're taking 0, 1 to the n, which is our old universe, and we're turning it into 0, 1 to the z1 cross 0, 1 to the z2. So that would be the sort of lifted case. And now each clause will turn into a combinatorial rectangle. Each clause. So the false assignments are just a cube. Turns into a combinatorial rectangle. Right? And that's pretty easy to see. OK, so so this works, but it turns out that general combinatorial rectangles are much more rich than just subcubes can be. So while this transformation certainly turns a proof of this into a proof of this, and in fact what it shows is that from a proof system perspective, if I start with a resolution proof, this system can simulate resolution effectively. It doesn't necessarily preserve hardness, right? There's nothing, because this system can of course do reasoning outside of this case. But I'd like to point out that this was actually useful in some cases. So the exact same transformation works for cutting planes, transforming cutting planes into these things. And this is also known as feasible interpolation, right? So this allows us to use lower bounds on communication protocols to prove lower bounds on proofs like the cutting plane system, which, in fact, all known cutting planes lower bounds proofs come from this transformation. Right? So this is good on the one hand, but it's bad. It's good on the one hand, but it's bad in the sense that it doesn't preserve hardness. So what we actually want to do is preserve hardness somehow. So you think a little bit more, and then there's the second natural way, which is so we'll pick some hard function, pick a little function g that's Boolean valued.
So just to clarify there, you meant the set of false assignments to each clause defines a rectangle.
Yeah, that's right. Yeah. Under the partition, yeah. So the second step to try to preserve hardness now is to pick a g, some little gadget, and we'll just replace every variable with a copy of g on some fresh inputs, on some inputs from x and y. So replace each zi with g of x of I and y sub I. Okay, so So in the time I have left, I'd like to do two more things, and then we'll break. So first, there's going to be two things I'd like to show. So the first thing I'd like to show is that when you pick basically any g and you do the substitution, so up here it was very clear that if we started with a clause and we did the substitution, then you'll still get like a rectangle. But once I compose with a g, it's very not clear that it'll be a rectangle anymore, right? Because correlations inside the g can screw everything up. There's a bit of a kludgy way to get around this that everyone uses, but that's the one that we'll use too. Okay? I actually think it's not that kludgy. It's very natural when you think about it a little bit. But yeah. Now the second thing I'd like to argue is that, so if you remember this earlier step where you started from a rectangle cover and produced a monotone function, it's very natural to ask, if I start with some unsatisfiable CNF, I compose with this g, and I produce this rectangle cover, what does the function look like? And it will turn out to be label cover, which is cool. Okay. So in particular, it's in NP, which means that we're proving lower bounds for, not just arbitrary functions, actually very natural structured functions.
Can you repeat that statement again? I got a little lost.
Yeah, sure. So I was just saying that I'll prove it, but when you start with this unsatisfiable C, and you substitute in this gadget, and then you get a rectangle problem somehow, what function does it correspond to? It'll turn out to be label cover. Okay. So first things first, how do we turn this into rectangles? So, okay. So let's just do an example. So we're going to start with over z variables, sorry. So we start with like a clause over z variables. And if you'd like a concrete example for a g that we usually like to plug in, the nice thing to do is to pick something that's like hard for communication complexity. So inner product is a good example. Another really popular one is the index gadget. So say the index gadget. So what it's going to do is it's going to map, I like to write it like this. Lambda is like a number. And all it does is it just indexes into y whatever x was. Okay? Okay. So after we do the substitution, we're going to get a clause like this over, should be ors, over these g's. And now just taking, yeah, so now, I mean, the partition is very naturally defined, right? One side of the partition will be the x variables. The other side of the partition will be the y variables. But it's very obvious that this won't necessarily be a rectangle anymore. Like the set of assignments which falsify this is not going to necessarily be a rectangle because it totally depends on the definition of G. And in fact, if you work it out, like only trivial G's will give you a rectangle, like a constant function basically, or a projection. So, okay. So how do we get rectangles? We're going to do it in sort of the dumbest way. So here's a picture of, so after doing a substitution, we'll get something like x to the n and y to the n, right? So this will be the natural partition. And now if I just look at one of these clauses and I think about what happens after I substitute these g's, I'm going to get like not necessarily a rectangle, but I'll get some kind of like funny shape. Right? These are like the set of assignments which, when I plug them into here, would falsify this clause, say. Okay? So the way that we'll turn this into a rectangle cover is just by breaking each one of these shapes up into rectangles in like a canonical way. So what we'll do is we'll just enumerate over all possible assignments to one side of these x's. And as long as the clauses are narrow, we won't introduce too many new rectangles when we do this breaking up. So it'll look something like this. Okay? So given a clause C and a gadget G to plug into one side, we'll define the rectangle that corresponds to it to be all the pairs x, y in x to the n cross y to the n. Oh, sorry, clause G, I meant to say are C and G, and also a third guy, alpha. So alpha is going to be an assignment to the x variables. So it'll be all pairs x and y, such that if I restrict x to the variables of the clause, we'll get alpha. And G of, if I take the clause and I evaluate it on the string G of x, y, it's falsified. Does that make sense? OK. So the size of this, so I'll call RC sub G. This will be like the rectangle cover. I'll call this the canonical rectangle cover. OK. And the size of this thing is going to be, well, I'll have a rectangle for every clause. And then every clause is then going to get broken up into rectangles that correspond to its width. So if C is a size m and width k, C and F, then the size of the rectangle cover will be like, at most, this, m times x to the k. Does that make sense? OK, cool. So this motivates, in particular, proving lower bounds for constant width CNFs in proof complexity. Because once you do this, like, if the clause is too wide, then this will become too big, and the number of variables will become so large that any proving exponential lower bounds in M is really, really easy. So it's sort of not interesting.
So what is this in x bars of C is equal to alpha?
Oh, I just mean that if I take x, which is a string, and just consider the projection onto the variables of C. So like in this case, it would be like x1, x2, and x3. If that's just alpha. So alpha is an assignment, like a local assignment.
Oh, I see. They're consistent with an assignment.
Yeah, they're consistent with some fixed local assignment. So every clause gets broken up further into the local assignments. Cool. Great. OK, so now I can tell you about label cover. Which many people here are much more familiar with it than I am, probably.
essentially?
You could restrict y too. There's no difference. Yeah.
And it's function, the y is much bigger.
It depends on the g. Yeah, that's what I was going to say. So like, what's nice about restricting, I mean, like, what's nice about only restricting to one side is that you can use like lopsided gadgets. You know, in general, we'll restrict to the small side because because the domain size is also going to show up here. And if you've heard, probably everyone here has heard Mika talk about this small size gadget problem because it's one of his favorite problems. The reason that the small size gadget problem is interesting is this x thing. This turns into the number of variables. So constant size gadgets means that the size of the rectangle cover, i.e. the number of variables in the function, is, yeah, like the size of the underlying CNF. So you get the tightest possible translation between proof complexity and circuit complexity. OK. So let's finally talk about label cover. There's like a million different variants of this problem, so I'm going to call it label cover because it's very closely related to it, but maybe people who work on PCPs and stuff will have different opinions. But it's different from it is a little bit different from the standard one that occurs from the standard definition. OK. So what we're going to have is a so the input will be a So we'll fix a factor graph in the background. So I just mean like a topology for the CNF for the CSP. So we have a bunch of we have a bipartite graph in the background where we think of one side as being the constraints, one side as being the variables, and then we'll have an edge if the variable is lying in the constraint. Okay. So this will be fixed, and this is the difference between the standard sort of label cover problem. So now the input is going to be a complete description of a truth table for every constraint. Okay? So if we have some alphabet in the background, which the constraints are going to be chosen over. So the input is going to be given by, for each constraint vertex, a truth table. So I'll call it T sub v. And what it's going to do is it'll map the alphabet on the neighborhood of whatever my constraint vertex is to 0, 1. OK? So the input is quite large. I guess it's exactly this large, right? So if x is my sigma, that's the size of the input. Okay? And now the output is, if you're given the CSP with these truth tables as input, with these truth tables describing the function, decide if it's satisfiable. So what's interesting about this is that it's a monotone version of SAT, right? So this function is monotone with respect to the definition of the truth tables, because the input to the function is just a truth table for every vertex. So if I flip a line from 0 to 1, I'm making the CSP easier to satisfy. So any satisfying assignment that was there before will still be there afterwards. So this is like a monotone version of SAT, right? And now the claim that we'll prove is that, in fact, like, if I start with an unsatisfiable CNF and a gadget G, and I look at this canonical rectangle cover, it will correspond to an instance of this label cover problem. Now, the factor graph will just be the factor graph of the underlying CNF formula. And the alphabet will be x, whatever Alice's input or whatever side you pick from the gadget. Okay? And then there will be a very natural mapping from from Alice's inputs to ones to satisfying instances, and 0 inputs to unsatisfying instances. Okay? Okay, cool. So maybe I'll just write it like this. So this label cover. Okay. So for any unsat CNF-C and any gadget function G that's Boolean valued. The canonical rectangle cover is the MKW game. Of some label cover instance, where the constraint graph will be C and the alphabet will be X. Okay. Okay. Well, the proof's actually going to be pretty easy. I mean, what you should think of is that the type of instances we're going to embed are basically going to be, in the yes case, the instances will be very simple. They'll just correspond to the CSPs that have exactly one satisfying assignment. So for every assignment to all of the signal variables, for every total assignment, there will have one yes instance where that is like the unique satisfying assignment. And the truth tables will correspond exactly to that. The no instances, on the other hand, well, they'll just be this. We take our CNF, we compose it with the G, and we just call that, we just embed that as our no instances. And for different assignments to the Y variables, we'll get different evaluations of what this G can look like. Okay. So the factor graph is the same as the factor graph for C, for the underlying CNF. The alphabet is just going to be these, whatever Alice's input is going to be. Okay. So now let's remember that the universe that we're mapping from is x to the n cross y to the n. And we want to map this to like ones of label cover. And zeros of label cover. Right? So x's are going to map to ones and y's will map to zeros. Okay? I mean, this is really not a cross product, just to be formal. So in fact, hopefully the way things are lining up is relatively clear. So every input variable of this guy is going to be indexed by what? Well, it's going to be indexed by a clause. So Cx. So we'll have z, which is going to be indexed by some clause, some underlying clause of this formula. And some partial assignment to the variables which are occurring in that clause, right? Where the partial assignment is chosen over these x guys, right? But that, of course, corresponds exactly to every rectangle that's occurring in this cover, right? And now, so let's map x to the n is going to get mapped to the ones of label cover. So this will correspond to R sub C and alpha. So if you're given an input x, we output the CSP with x as its unique satisfying assignment. So what do I mean by that? We'll just take x, plug it in for all the variables, look at the constraint at its local guys, and that will be the only one that we'll set in that constraint. And it's easy to see that this will be like the unique satisfying assignment for this guy. Okay? So that's the ones. The zeros are a little bit more complicated, but not too bad. So given a y, which is like Bob's input, we want to map it to a 0 of label cover. Let's do it like this. Label cover 0. Okay. Well, I'll just define the CSP hopefully in a very general way. So so H, which will be my new CSP, this is just going to be literally C. This is my underlying CNF formula, where I plug in the g's for all the variables. This is like g to the n. So the free variables are the x guys, and I'll just plug in the y here. Right? So every y will get plugged in on the y side of the gadget, and my truth tables will be defined so that H is just exactly whatever this CSP is going to be. So take my unsat CNF and compose it with G. And then the free variables are the x guys, which of course satisfies all the types. So now, why is this a 0 input? Well, it's because C is unsatisfiable. So no matter what I plug in here, I'm going to get an unsatisfiable CSP at the end of the day. And it's not hard to show that this thing goes in reverse. So this is kind of remarkable, I think. If you start with this guy and you do this natural composition, you get a very natural function in NP, right? And it turns out that you can, maybe just to finish off with saying in words, it turns out that most of the monotone circuit lower bounds that exist can be phrased in this way. So the old lower bound of ST connectivity corresponds to taking this induction principle that I wrote down and composing it with equality. If you take clique, you could take a CSP, which is kind of a trivial CSP where you have k variables and they're from a universe of size k minus 1, and you want to say that each pair is not equal, right? So it's trivially unsatisfiable because there's not enough places for it to be different. And you can compose that with the index gadget, and you get clique coloring. If you take gen, you start with something called the pebbling formulas, and you compose them again with an index gadget or whatever your favorite gadget is, and you get this problem that's complete for P. And this proves this is like what Ross Mackenzie used. And then it turns out that there's more natural interpretations for other formulas as well. But yeah, I guess I'll stop there.